circuit diagram. So in fixed bias network, emitter is directly held at ground potential. Base is connected to resistor RB. Collector is connected to resistor RC. Okay, and the other two terminals of the two resistors is connected to positive supply voltage VCC. Okay, the equivalent circuit I have shown in figure B. Okay, this is figure A. Now in the equivalent circuit, what we have done is we have separated out the input circuit and output circuit. The base terminal is connected to RB. So base is connected to RB, right? The other end of RB is connected to VCC. So other end of RB is connected to VCC, the positive terminal of VCC. So they haven't shown the negative terminal. So it is understood that the negative terminal is grounded. So we have directly taken the negative terminal and we have connected it to ground. Okay, that's about the input circuit. On the output circuit, you can clearly observe that the collector terminal is connected to RC, right? So collector we have connected to RC. And other end of RC is connected to VCC. So negative terminal of VCC is once again grounded. So this is your equivalent circuit. And then you mark the respective transistor currents. Towards base, IB flows. Towards collector, IC flows. And from the emitter terminal, emitter current, IE flows. All right. Once you are done with marking the currents, you can mark the terminal voltages. So voltage measured between base and emitter is taken as VBE. Okay, base is held at higher potential, hence plus sign is given, and emitter is kept at ground potential, hence minus sign is written. Similarly, on the output side, you have a second terminal voltage that is measured between collector terminal and emitter terminal. All right. The collector terminal, if you observe carefully, the collector is connected to positive terminal of the battery. Hence, collector will be at higher potential compared to the emitter terminal. All right. So this is about your marking of voltages and currents. Is it clear?
Yes, sir.
All right. Once that is done, we can go for analysis. As you can expect that you will have two loops, right? So, two types of KVL equations you may have to write. Okay. So this is my input loop. Okay. What I will do, I'll just write this as input circuit. And this is my output circuit. So in transistor, normally what I do is, for the input loop, I apply KVL in clockwise direction. Okay, clockwise direction. Okay, why clockwise? Because I'm just trying to follow the battery direction. That's all. Nothing sci-fi is involved in there. On the output side, what I will do, I will normally apply in anti-clockwise direction. I'm just taking the battery current reference, that's all, okay? So that, I find it very convenient, okay? All right, so this is how I choose the path for applying KVL. You can take the opposite path also, doesn't matter. I cannot, do so many permutation and combination. So if at all I apply KVL, I apply KVL in clockwise direction for the input circuit and anti-clockwise direction on the output circuit. The reason is I just want to follow the battery current convention. That's all. All right, fine. So in the analysis, what you do is apply KVL for the input loop. Okay, so this input loop is also called as base emitter loop. Okay, because in common emitter configuration, base terminal is the input terminal collector terminal is the output terminal, and emitter terminal is the common terminal. All right. So base emitter loop is nothing but input loop. So in future, I may call sometimes apply KVL to BE loop. It is understood that BE loop is your input loop. Right. So let's apply KVL. Let's start from the battery itself. -2 plus. Okay, in clockwise I'm going to go. All right, -2 plus is plus VCC, and then you have IB into RB. So that drop is taken as negative, minus IB into RB, and then you are encountering the terminal voltage VBE. So plus to minus, the voltage is getting traced, hence it is minus VBE. Okay, and then there is no element connected between emitter and negative terminal of the battery, hence I will stop my KVL. Okay, so only 3 terms you are going to get. Or the base current IV is equal to difference in potential, that is VCC minus VBE divided by RB. So this is my base current equation. Base current equation, where VBE is 0.7 volt for silicon transistor and 0.3 volts for germanium transistor. Okay, germanium transistor. That's because it's an NPN transistor. No, it's an NPN transistor. This is your N layer, this is your P layer, and this is also your N layer. So on the input side, basically you are measuring the voltage between P and N layer. So this P and N layer can be considered as a diode layer, diode PN junction you can consider. So you know that in a diode, for a silicon diode, the potential between P and N layer is 0.7. So in the similar sense, I have written VB as 0.7 for silicon and 0.3 for germanium. All right. So that's your base current. Having known base current, okay, you can find collector current using the formula IC is equal to beta times IB. This is your second equation. This is your first equation. This is your second equation, where beta is equal to current gain of CE mode. Okay, so normally beta value is given. Okay, they'll give almost every time they give the beta value. Okay, only in few exceptions, they don't give beta value. If they don't mention beta value, we can choose beta value. Okay, so fine. So that's about your input circuit. So input circuit basically enables you to find the base current as well as the collector current. Okay, now you can apply KVL. Okay, so you can write apply KVL to the output loop. Okay, output loop, sometimes I may call it as CE loop. Collector to emitter loop will be my output loop. All right, CE loop. Okay, let's apply KVL. And which direction I'm going to apply? In the anti-clockwise direction. So -2 plus VCC, then IC into RC drop. Along the current direction, the potential drop is taken as negative, and then +2 minus VCA. So -2 plus, then the drop, then +2 minus you have. So when you apply KVL, you will get VCC minus the resistance drop minus the terminal voltage is equal to 0. Okay, so using this formula, you can find out the VCE value. What is VCE? VCE is equal to VCC minus IC into RC, where IC value is given from equation 2. Okay, so this is your third equation. That's all. This is the simplest analysis. So if you know the resistance values, you can just substitute and you can find out the IC value, VC value, etc., etc. Fine. So this is about the analysis. Okay. Once the KVL equations are known to you, you can go for a second type of analysis, which is very important, which is called as load line analysis. load line analysis. Okay, now load line analysis. Okay, load line is a straight line. Okay, load line is nothing but a straight line drawn on transistor output characteristics. Transistor output characteristics. Okay, so let's see how to construct this load line. That's what I was saying, right? In the introduction class. Let me teach you the load line concept. Here I'm going to tell you the load line concept. All right. So load line is a straight line which is drawn on the transistor output characteristics. So to draw the load line, you have to take transistor output equation, transistor output KVL equation. KVL equation. And what is that KVL equation? That is equation 3. Equation 3. Okay. So what is it? VC is equal to VCC minus IC into RC. Okay. Now there are two output variables, right? VCE is the output voltage and IC is your output current. Output current. Now, in order to draw the load line, you must have some x-intercept and some y-intercept. Okay, but how to find these x and y intercepts? Because there are two variables, right? So whenever you have two variables in mathematics, what you have to do is you have to substitute one variable as 0 and find the other variable and do vice versa. Okay, so what we do is when you have two variables, first, let us say, okay, I would say VC is equal to 0. Say VC is equal to 0. When you put VC is equal to 0, okay, VC is equal to 0, and substitute this in equation 1. Okay, what do you get? You get LHS as 0, and on the RHS, you are left with VCC minus IC into RC. So that implies VCC is equal to IC into RC. So this enables you to find the collector current IC. And collector current IC is nothing but the voltage to resistance ratio. That is VCC divided by RC. What is it? This is IC. And this is also called as IC sat or IC saturation. Okay. And this IC saturation going to be the y-intercept. Y-intercept. All right. So let me just color it with a highlighter. Okay, intercept. All right. Similarly, now let us put, say, the other variable as 0. That is, we'll put IC is equal to 0 and substitute in equation 1. Let's see what we get. When we put IC is equal to 0, you will get VCC. Sorry, yeah, right hand side VC, right? VC is equal to VCC. Since VC is equal to VCC, and VCC is the power supply voltage. Okay, this is power supply voltage. This is power supply voltage, DC power supply voltage. So sometimes this VCE is also called as VCE saturation or VCE sat. So VCE sat is equal to VCC, the power supply voltage. Okay, so this will be your x-intercept. X-intercept. All right. Now join x and y intercepts. So when we join x and y intercept, we get the load line. Okay, so let's do that. So what I will do, I'll go to shapes, quickly draw the axis. We draw the x-axis, and let me mark the axis. This is IC, and this is VCE. Okay, so let's mark the y-intercept. Let's say my y-intercept is somewhere here. Okay, and what's the value of y-intercept? IC saturation, which is equal to VCC by RC. Similarly, let me also mark the x-intercept, and value of x-intercept is VCE sat, which is equal to power supply voltage VC. Okay, and then you join the 2 points with a straight line. Done. Okay, so that's your load line. Okay, so this is called as the load line. Load line. Okay, and the slope of the load line M is equal to minus 1 by RC. Okay, it's a negative slope in the sense the line is, it is kind of downgoing ramp. From the maximum value, the slope keeps on reducing. Okay, so that's the reason it is minus. Okay, how did you get this slope as minus 1 by RC? Okay, so right, instead of how, y M is equal to minus 1 by RC. Okay, I'm going to give you a proof also. Equation of a straight line. What is it? Equation of a straight line. Y is equal to mx plus c. Right. So this is my standard math equation for the equation of a straight line. Now, what do we have in our output circuit? In the output circuit, we have our output equation, which says VCC minus ICRC minus VCE is equal to 0. So let us rearrange. Okay, so let's say this is equation 2. So rearrange equation 2. Okay, so what I will do, I want to have my y coordinate on the left hand side, and I want to bring my x variable on the right hand side. So let me just rearrange the equation. So what I will do, I will write minus IC into RC. I'm going to keep this product in the left hand side, which is equal to, let me bring VCU on the other side, okay, as well as VCC. So this is minus VCC. Okay, so VCE, when it comes to right hand side, it becomes positive, and the positive VCC becomes minus negative. Okay, or let me write IC is equal to, okay, what do we have? IC is equal to VCE. Okay, it is minus VCE divided by RC. Okay, and then minus VCC divided by minus IC. I'm sorry, this is IC, right? This is IC. I have to divide. So when I divide, I have to basically divide with the RC here. Yeah, this is RC, and this is also RC. I should have erased the second part. This is also RC. Okay, or IC is equal to minus, let me just separate out, 1 by RC, okay, into VCE plus VCC by RC. VCC by RC. Okay. Now, what is Y? Y is your collector current, right? Along y-axis, you have projected collector current. So Y is equal to, this ratio is your M. And VCE, what is VCE? VCE is your X variable. So Y is equal to MX plus C. So C is the ratio VCC by RC. Okay, so now if you, okay, let's say this is equation 3. So compare equation 3 and equation 1. What do we get? When we compare equation 3 and equation 1, in place of y, we have IC. In place of x, we have VC. And in place of slope m, we have minus 1 by RC. So we get slope m is equal to minus 1 by RC. Okay, so this is the proof. That's the reason I have written the load line is having a slope of minus 1 by RC. So this is also called as conductance, right? Because reciprocal of resistance is conductance. Okay, fine. So that's about the load line. Now the operating point, you know, can be here or can be here or can be here. So this is the region for operating point. Operating point. Okay. So on the load line, the operating point is fixed. Should it be fixed on the center or should it be fixed in the saturation or cutoff region? That solely depends on the end application. For switching operation, you have to operate the transistor in saturation and cutoff. And for amplifier region, the operating point should be fixed at the center of the load line. All right. So that's about the load line analysis of fixed bias circuit. Okay, fixed bias circuit. All right. So what I will do is I'll do the derivation, and in the meantime I'll solve the problems as well, so that you know the theory and problems go hand in hand. So let us solve a problem. So problem number 1. Okay, so this problem I have picked from Boyle-Stead textbook. Boyle-Stead book. Okay, that's the reference book. BLE. Okay, BLE, Boyle-Stead book. Fine. So the problem says, for the circuit shown below, determine the following: IBQ, ICQ. Second one, VCQ. Third one, VB and VC. Fourth one, VBC. Okay, and this is the given circuit. So that's VCC, for supply voltage is plus 12 volt. This is resistance RC, 2.2 kilo ohm. RB, 240 kilo ohm. I'll just class ಕೆಳಗಡೆ ಬೇರೆ ಹತ್ರ ಕೇಳಿ, ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಇದ್ದೀನಿ ನಾನು. All right, and they have also mentioned that the beta, transistor value beta, is 50 and a silicon transistor. Fine. So this is the given problem. Okay, so you are supposed to find IBQ, ICQ, etc., etc. Okay, so what I'll do, I'll quickly draw the equivalent circuit. This is my ammeter. RC plus minus VCC connected to ammeter terminal, and which is maintained at ground potential. So this is RC, which is 2.2 kilo ohm. Okay, and this is the base terminal connected to RB, and RB is connected to again VCC, and VCC is 12 volts. So this is VCC, which is equal to 12 volts. Okay, this is your base emitter voltage. Lower side negative, upper side positive, and this is your VCE, upper side positive, lower side negative. Okay, fine. Next, you apply KVL. KVL to input loop. Okay, so you will get IBQ is equal to VCC minus VBE divided by RB. Okay, IB or IBQ doesn't matter. Okay, you can either write IB or you can write IBQ. I'm writing IBQ because in the problem statement they have given so. So IBQ is equal to VCC minus VBE divided by RB. The equation I have already given in the theoretical analysis, right? So IBQ is equal to VCC. What is VCC? 12. What is VBE? 0.7 for silicon transistor, and RB is 240 kilo. Okay, that is 10 to the power 300. So IB, when you substitute, you will get 47.08 microamperes. Okay, fine. So that's IBQ, first part, right? And also you are supposed to find ICQ. ICQ is beta times IBQ. So 50 times the base current. So it is 50 into 47.08 microamperes. Okay, so that you will get it as 2.35 milliamperes. Okay, fine. So that's the first part. Okay, second part, you are supposed to find VCQ. So we have an expression for VCQ from the output circuit, right? So VCQ is VCC minus ICQ into RC, which is 12 minus ICQ. Okay. We have found that ICQ is 2.35 milli into RC. RC is 2.2 kilo, so 10 to the power 3. So milli and kilo gets cancelled. So basically you will have VCQ as something like 6.83 volts. So that's your VCQ. Okay. So having known VCQ, you can proceed to find the third part. So third part, what is it? VB and VC. VB and VC. This is pretty interesting. In the beginning, I said potential difference needs to be measured with respect to 2 points. But in the question, they have just given VB. That is potential difference base and what? They haven't mentioned base and the other terminal they haven't mentioned. So it is understood that whenever they use single subscript notation, VB stands for base to dash terminal, base to ground terminal. Whether given or not given, if someone gives a single subscript notation, it is understood that the invisible terminal is your ground terminal. All right. Similarly, VC means collector to ground potential. Okay. Given or not given, this is what you are supposed to know. All right. Fine. So let's mark VB. VB is what? Base to ground. Okay. So base to ground is this. Base to ground is this. On the other hand, collector to ground is this. From collector terminal to the ground terminal. Okay. I have marked base to ground and I have also marked collector to ground. Now you tell me what is VB and what is VC. For your understanding's sake, let me connect a voltmeter. One terminal of the voltmeter here I will connect and the other terminal I will connect it to ground. Okay. So base to ground, what do you find? So between base and ground, you have the terminal voltage VBE coming into picture. So basically your VB is nothing but VB, and between collector and ground, okay, between collector and ground, if you look at, erase this, okay. I'll erase everything here. What I will do, I will connect a voltmeter. So this is my voltmeter. One end of the voltmeter is connected to collector terminal and the other end of the voltmeter is connected to the ground terminal. Okay. Now you have to also understand the fact that the ground terminal itself is emitter terminal because emitter is directly connected to ground terminal. So in this case, the output voltmeter reads potential across collector node and ground node, which is nothing but collector node and emitter node. So VB is VBE and VC is VCE. So VB is 0.7 volts and VCE is, how much did you get? 6 point something you got, right? 6.83 volts.
83.
Right. So that's your base to ground voltage VB and collector to ground voltage VC. Okay. And in the final part, probably you can find VBC. Okay. So VBC. Okay. So when you say VBC, base is considered at higher potential and collector is considered at lower potential. So VBC is simply the difference between base voltage and collector voltage, which is nothing but 0.7 minus 6.83. So that gives the voltage as minus 6.13. Okay, so that's your solution. Okay, so such problems, can come for 8 to 10 marks. 8 to 10 marks. So each part will be contributing about 2 marks each. 2 marks. All right. So that's the first part of the problem. Okay. Okay. Is it clear? Is it clear? Okay. Second part, load line. Okay. This extension I am only creating. Okay. So question 2 I will make, and I would say plot the load line analysis. So to plot the load line analysis, what you need IC saturation, and you also be needing VCE saturation. So from our previous understanding, you can write IC saturation as VCC by RC. Okay, what is VCC? 12 volts. What is RC? 2.2 kilo ohm, right? So into 10 to the power 3. Kilo is 10 to the power 3, right? So what do you get? 12 by 2.2 will give you current as 5.45 milliamperes. So 5.45 milliamperes. So that's your saturation collector current. And we see saturation from the theory. We have seen that VC saturation is VCC and VCC is 12 volts. So these are your coordinates of the x-intercept and y-intercept. Okay, so having, calculating the two, you can plot the load line analysis. Okay, this is your IC, this is your VCE. Okay, some nominal scale I'm going to take 2, 4, 6, 8, 10, say 12. Okay, so that I get kind of, say 1, 2, 3, 4,